just like this test with a concrete column, are usually extremely costly, and some experiments are not even feasible at all when you deal with high explosives. Just imagine you have an internal detonation in a bunker system. I don't have a bunker system in my garden, so it won't be easy. So generally, the application of numerical simulations is an integral part of today's assessment activities, not only for high explosives, but in all kinds of research and development. So, for high explosive detonation simulations, we usually use hydrocodes. A hydrocode may be loosely defined as a code for solving large deformation, finite strain, transient problems that occur on a short time scale. This is actually the definition given in Benson. I can only recommend this down here to everybody who wants to get into the hydrocodes. It's part break, it's 160 pages, mainly mathematics and physics. But once you're through this, you know pretty much. So, hydrocodes have originally been developed for the simulation of nuclear blast after the Second World War. So, these were mainly hydrodynamic calculations where strength was not of interest at all. Later on, constitutive models to incorporate strength were added. So now we can simulate not only hydrodynamic events, but also strength effects of all types of materials that are loaded on short duration. Generally, there are two descriptive methods in the hydrocodes. There are more, but the most basic ones are the Lagrangian and the Eulerian. So, if we have a look at this problem, the dinosaur jumping into the pool, we can look at this problem in two different ways. The first is the Lagrangian way. So, we mesh the dinosaur, keep the mesh on the dinosaur, so it's a body-bound mesh, and when we hit the ground, the mesh will undergo deformations, and in some cases extreme deformations. And the second way to look at it is to keep the mesh fixed in space and let our dinosaur actually jump through the mesh. So here the material goes together with mesh, here the material goes through the mesh. Two different points of view should theoretically result in the same or give the same results. However, if we have very extreme deformations of our elements, things become unstable and our simulations slow down or even stop. So when we try to simulate detonation events when we have extreme deformations, we usually focus on the Eulerian description. And this is what I'm going to talk about in the next slide. So, governing equations. When we want to simulate this material going through the mesh, in hydrocodes, we generally build up on the balance equations for mass, momentum, and energy. Everybody should have seen the three balance equations in some form at some time. Here, this is already the Eulerian description. So we are thinking we have a constant volume and we have material maybe going in and going out of our volume. However, if we have these three basic balanced equations, if we want to simulate our detonation events, there's still something missing. Because with these three equations, we cannot solve the Rankine-Hugino equations. So what we need is an additional constitutive description or constitutive relation to describe material behavior. This here is nearly independent from the material, because acceptable density. So, in the hydrocode, the volumetric and deviatory stresses, so these constitutive descriptions, are treated separately. We have two different separate constitutive material laws. Why? Well, first thing is simply from history, because hydrocodes began with hydrodynamic calculations, so from the complete description here, where the stress tensor T is actually a function of strain, strain rate, energy, and damage. Initially, only this part was regarded, the pressure part. So in hydrocodes, the complete stress tensor is split in the volumetric, the pressure part, and the deviatoric part, deviatoric stresses. And we have the constitutive relations for these two parts. So, for the volumetric part, we have the so-called equation of state, usually pressure as a function of volume and energy. And the deviatoric part, pressure subtracted from the complete stress tensor. What is left is the deviatoric stress tensor, and we have a constitutive description for this deviatoric stresses. But for our explosives, we do not regard strength at this moment, so we will concentrate on the equation of state. The equation of state is actually some kind of surface in the PVE space, pressure, energy, specific volume, and it describes all states the material can take. Now, if we shock our material, we do not go through this curve, this isentrope, but we directly jump from the initial state along the Rayleigh line to the final state after the shock. We don't go through this isentrope curve, we jump on the Rayleigh line. And this type of curve can be determined in, for example, fireplate experiments, and then you have a relation here. And regarding the energy direction, there is usually an extrapolation made, which can hardly be measured in the experiments. So, a few words on CJ theory. We keep this in mind. We see the black line. This is actually the Hougonio of the explosive, which is here, blue line. And we start at V0, and we want to jump up to a certain pressure state on the solid Hougonio of our explosive. In CJ theory, we don't reach this, but we stop at the CJ state, we jump to the CJ state, and we're on the Hougonio of the detonation products. And from that point, the CJ state, we go along the expansion isentrope through the CJ state. The Rayleigh line is thereby assumed to be tangential to the Hougonio curve in the CJ point. And this results in a single solution for the detonation velocity, which is actually partly defined by the detonation velocity. If we look at this here, we see the density. This is a fixed value, the initial density. So the detonation velocity defines the slope of the Rayleigh line. So now we want to model our explosive. Usually, explosives are modeled with the so-called Jones-Gutierrez DJWL equation of state. This equation of state applies a Knie-Grüneisen form as the basic form and uses the isentrope as a reference curve. What is this exactly? So, what we have here, pressure as a function of specific volume and energy is the isentrope plus an extrapolation into the energy direction in the plane. Jones, Wilkins, and Lee assumed the isotrope to follow this form, which is actually just a mathematical approach to capture the isotrope. With A, R1, B, R2, C, well, C all the way, and omega being model parameters. The reference energy is then the integral of our pressure along the specific volume. And if we do this integration, we come up with this term here, where the capital V is actually the scaled specific volume. And with these two equations here, if we now put them into this form, both put them in here, after a short calculation, we end up with the actual JWL equation of state as you will find it in literature. Here again, with the parameters A, R1, omega, E, and R2. The question now is, where do we get the respective parameters, these 5 parameters from? This is usually done with thermochemical calculations. And numerics, we have our in-house code, Dragon, which is relatively simple after we have done all the work for the library. So the input here, the only thing that is done is you have the density of your explosive and the mass percentage of the constituents, like RDX, HDDB, or aluminum, whatever. And together with the library information, the formula, the column, enthalpy, the mechanical US, and so on, we can finally obtain, for example, the CJ state, the complete a list of reaction products with the respective percentages. This is thermochemical calculation, nothing more, or complex enough. We can output the CJ isotopes in different variants or descriptions, and we also receive the JWL parameters. This is, in most cases, already a good parameter set, but nevertheless, it has to be calibrated against experiments. So, for the calibration, we usually do not use these plate dent tests, because these plate dent tests require knowledge on the strength, on the constitutive model of the plate. Here, strength plays a significant role, as it was already said. So what we usually use is the explosive cylinder test, where a soft metal cylinder, usually copper, but also steel, is detonated, and the cylinder expands, and what we actually measure is the expansion velocity at different times, or the expansion at different times. So here's a setup for detonation velocity. Here's a typical cylinder test setup. The balloon here, that's argon, it's an argon flash to deliver the backlight during the test. And what we actually do is we use a street camera which looks through this slit here and nothing else, just through the slit. And the film is pulled and we come up with something like this. So this is the time direction and this is the film pull direction. And here we see the distance. We have the initial distance of our cylinder, and with time it expands. You can evaluate this with a ruler, but we prefer a more precise method with another in-house software with edge detection and images. We determine actually this slope here, we have some marks of the distances so we can exactly know the dimensions. And we have some scaling points. And when we've done this, we can plot our results into a diagram, simulate the cylinder test. If necessary, we can refine the material parameters, and we are done. We're having a parameter set for a high explosive that is actually applicable in most applications and simulations of the high explosives. For example, we can use it for typical blast simulations. Here, you see nothing, great. Over here, also not. Okay, blast simulations. This was the simulation of bomb blasting in the center of Munich in 2012 in August, and in metal pushing like shape charge jet formation, here with a HOT anti-tank warhead. But please keep in mind that accuracy does not only depend on your model, but also on the implementation of the model. Code, it's not that straightforward as one might expect. And it depends on the code itself. Some codes have advection schemes, first order, second order, third order. This will make a difference in the accuracy of your results. In the case of speed, this is a reference example where a PSTA charge was detonated above ground and shearing images were taken. And as you can see, this is the simulation here. Practically all phenomena of even complex shock structures can be represented if your code is capable of doing this. Mach stem development down here from ground, multiple reflections, slip lines, and so on. So far for the JWL alone. Let me now come to aerobic afterburn. What is anaerobic afterburn? What is anaerobic afterburn? In some cases, explosives are designed to carry their own oxidizer, or to have additional aluminum that will then take away the oxygen from the reaction products to oxidize themselves. Typically it's aluminum that's very aggressive and takes away a lot of oxygen. And this is typically applicable where no air, no oxygen is available in the atmosphere. For example, underwater explosives. The approach is very simple. We have a time-dependent extension to the JWL equation of state, the so-called time-dependent JWL, or the Miller extension, where simply specific energy is added to the energy term of the JWL. Here is this lambda Q. And this energy is not released instantaneous, but time-dependent. Because the oxidization of, let's say, aluminum takes time. This is not something that happens directly together with the detonation event, but it may take a few milliseconds for the aluminum to oxidize. So, the supply of this additional energy is controlled by this energy Berg fraction lambda. And in the Miller extension, or time-dependent JWL, this burn rate is formulated as relatively simple power law, also depending on the current pressure. The Q, the additional energy itself, is usually again taken from thermochemical calculations. And the calibration of the parameters A and N is something that is not very easy, because you need to make sure that you don't mix effects. If you detonate it in a closed detonation chamber, for example, you can never be sure if the aluminum is burned by oxidization in the atmosphere with air, or if it's actually the anaerobic afterburn, where the detonation products are reduced and the aluminum is oxidized. So the best thing to do this is actually underwater detonation tests, and those will give you a reference to which you can calibrate your parameters. Application example. Here we studied the detonation of a World War II water bomb near the coast of the East Sea in Germany. And we actually had to determine safety ranges for the disposal of these bombs by blasting them underwater. As you can see, they have 125 kilogram torpex filling. And simple approach, we model the bomb, we place it on the ground. In this case, as we have larger distances we want to observe, it doesn't make a difference if you lay it on the ground, if it stands on the ground, or whatever, because if you go far enough away, it simply doesn't make a difference anymore. It was put on the sand with some rock underneath, and first of all, we had a look at the initial detonation of this thing. Once we had this, we took the model and mapped it into our large-scale sea. Here. So, we're down here with our bomb, and this is a meter scale. Just a rough one to show you as an example. Oops, that was not it. Nothing to see, it's just pressure wave running through. And so what we get when we have simulated this is a pressure time history, and we have already seen something quite similar from the experiments. This is the numerical result. Again, we have here the bubble period. And this is especially important for the calibration, because the peak pressure is related to the JWF. It has nothing to do with the Miller extension, because this comes later. So first of all, we have to match the peak pressure, but the Miller extension actually controls this bubble period. So if you want to calibrate your Miller extension, this type of underwater detonation experiments is very valuable, since here you really have data you can work with. There is no disturbance by the existence of air, and the additional energy significantly influences the bubble extension and bubble period. And here you have something to work with. Another thing I came across is an effect called bubble jet. And this is, well, let's call it an excursus. It's not directly related to project work, but I thought this was interesting to show. So what we see here is a torpedo blast test. And we see two things. We see a first shock, but this is not what destroys the ship. There's somehow a water jet coming up, cutting the complete ship into two pieces. Once again. I really love this. This was actually the Australians who did this test, and the ship was American. So they did nothing wrong, not blasting their own equipment, but you see it's actually cut in two halves. So where does this come from? And I simply wanted to know if I can see this in a speed simulation too. And here's a large-scale detonation of KS-57. This is the underwater explosive from PDW. And this was tied to some other project. But when I had a look at it, I could find that here we have the first bubble, but after this, the collapse and the lifting up of the bubble causes this jet. And this jet is actually what kills the ship. So torpedoes don't have to hit the ship. It's even better if they detonate underneath the ship. So that was only short excursus. Now we come to the aerobic combustion. Aerobic combustion is pretty well known from the so-called enhanced blast explosives, these aluminized explosives that make bright fireballs and they look so good. But aerobic combustion is something we encounter with practically every explosive. If we have a look at the oxygen balance of simple TNT, we see that we have 33 to 34% under-oxidized products. So, what happens? We have the explosive, and it detonates, and we come up with the oxidized detonation products, and with quite a lot of under-oxidized detonation products. And this here still has a lot of energy. So when we take this and oxidize it, and take it as fuel and oxidize it to the oxygen in the air, we come up with the so-called combustion products and significant additional release of energy. Again, not instantaneous with the detonation. It's a time-dependent thing. Also, usually going over several 10, 20, 30 milliseconds. But the energy is really significant. So, how do we approach this? In speed, the combustion model is based on the general approach suggested by Kuhl, so that combustion is actually controlled by turbulent mixing of the detonation products with air. You need supply of air for your detonation products to oxidize. Basic requirement. Further on, we assume that there's a certain threshold temperature which must be exceeded to activate or maintain, respectively, the combustion process. And finally, as an implementation assumption, we assume that the reaction takes place instantaneously whenever detonation products and air occupy the same computational cell. So this is what I tried to show here. The other one is detonation products. They enter the cell filled with air, and according to the mixture, directly converted to combustion products. So, if we have a look at the mathematical formulation, the modeling of this, yeah, it's probably now it looks a bit better. Here we have the JWL equation of state, and we have the ideal gas equations for the detonation products and the combustion products. Now, we take the stoichiometric mixture and see what we can make out of the materials we have in the cell. We have a certain amount, a certain mass of detonation products, with a certain mass of air, with a certain mass of oxygen. And once we have gone through this equation, either the extent, the mass fraction of the detonation products, or the mass fraction of the air is zero, because either all available air is used up, or the available detonation products are used up and are converted into the combustion products. Here's the respective energy equation. I won't go into this. It's basically the same as here with the mass fractions. So, looks pretty simple. It's a relatively simple approach, but it will turn out to be working quite well. So here an application, this was an internal detonation test at the ICT in Karlsruhe. A 45 cubic meter detonation vessel with a 2 kilogram charge of KS22A, was hung up in the middle. We had a plate at the bottom and pressure sensors, PCP gauges around here. So we simplified this model into a 2D axisymmetric model with the same volume. We took our KS22A JWL parameters, which we were calculated from Dragon again and verified by multiple test data, and the combustion model parameters also taken from thermochemical calculations. So what is the additional energy we can get out of the combustion products or out of this reaction? And the simulated thing. And we see the yellow, that's the detonation product.